Okay, so we have just analyzed a new genome, in this case E. coli K12, and we are ready to do single gene or locus targeting using Casper. So you see that we can select organisms and endonuclease pairs that Casper recognizes from within this Casper DB directory. And we can also choose annotation files also located within that directory. If for some reason we did not download the annotation file when we created a new genome, we can download them now using the NCBI tool again. You can see here it's the same searching from the previous video where we created a new Casper database from the E. coli genomes. So we don't need to do this again. We already have the annotation file right here. So for searching, it's very simple. You have the option to input a variety of things to find the right gene. Either ID, locus tag, common name, or even a description of the gene will work. For position, all you have to do is provide a comma-separated line with chromosome, number, start location, stop location. So we can start with that really quickly and show you chromosome 1. Let's say start with location 1 and go to location 200. Then we click Find Targets, and you can see it's already loaded, so we can click View Targets, and we see that in that location we have 8 different guide RNAs. And the endonuclease that they belong to, their full sequence, the strand direction, the PAM, the score, as well as off-target details that are waiting to be added in should we choose to run it. So we can go back and instead search for things on a gene basis. So let's say that we're interested in a DNA polymerase. So we can type in DNA polymerase. And Casper will search the provided annotation file for all mentions of DNA polymerase. You can see here. Now if we wanted a particular gene, let's say DNAQ, we can type in just DNAQ. And then that will return only the entry for DNAQ. In order to select a gene, all you have to do is click on the row. So let's say maybe we want to look at all polymerases, and we just type in polymerase. Now we can see DNA polymerases mixed in with RNA polymerase. Here we have an ECA oligosaccharide polymerase, and you can actually select multiple rows to analyze. So let's look at an RNA polymerase sigma factor and a DNA polymerase 3 subunit. We'll do subunit chi. And all we have to do is click submit. Now Casper pulls the guide RNA targets for these genes and allows you to either generate libraries of guide RNAs for them or view the targets individually and pick out custom which ones you want to keep. So we'll do that for now, and we'll generate library in a different video. So here you see the genes we selected. It looks like I actually selected an additional gene, subunit alpha, by mistake, but that's okay. You can switch between the different genes, and the information in the table will automatically update itself. You have, if you have generated multiple CSBR databases for the same organism using different endonucleases, all of those will show up here, and you can switch between endonucleases just by clicking the different options on the dropdown. This is especially useful for instances of co-targeting, which we cover in a later video. On the right side here, we have a gene viewer. And so basically, all you have to do to see the gene that you're targeting is click Display On. And that will show you the actual sequence of the gene that you're targeting. And you can then click on the guides in the table and highlight where they are appearing in the gene of interest. Red indicates that it's a negative strand. You can see here the NGG is on the 5' end because it's a reverse strand guide. And you can also sort the table. So if we wanted to look at a positive strand guide, we could first, I guess, clear the guides and then highlight this one. And we see we have a nice forward strand guide before this AGG PAM here. Now we have a couple of filter options. If, for instance, you wanted sequences with only 5' Gs, you can click that and it will pull out the sequences that begin with G. This could be important for certain promoters that only express guide RNAs with a 5' G. Also, we have the option to view co-targets if co-targeting is feasible for the selected endonucleases. And then we have a minimum on-target score that can be controlled with this slider. Let's say that we want the minimum score to be 50. We can slide it, and now our table will only contain guide RNAs with scores over 50. Lastly, let me get this back to 0. Lastly, we have off-target and co-targeting analysis options. So co-targeting, if you try to do it with just one endonuclease, you'll see that there are not enough for this organism. So you need at least 2 endonucleases that with compatible PAMs to use the co-targeting function. Once again, this will be covered in a later video. Off-target works off of selecting rows from the table. So you can either select all or just select a handful. Let's select 5, and then we click off-target. Now off-target analysis will prompt us to select a reference, either any of the organisms that we've generated a Casper database for can be used as a reference. So since we've only made one file so far, we'll have to stick with E. coli. So this will be looking for off-targets within the same genome. The different parameters for the off-target algorithm are given here with different descriptions available on hover. Tolerance is essentially a measure of how nitpicky you want the algorithm to be. So if you set the tolerance to 0, that means it'll catch everything, no matter how minuscule. If, however, you're not worried about off-targets with scores smaller than, say, 0.05, you can click up the tick box, and basically anything below 0.05 will be considered a non-hit, and it will be counted as 0. This can speed up the performance of the off-target algorithm. Similarly, if you want to reduce the search space, you can limit the number of mismatches that the off-target algorithm takes into consideration. So if your max number of mismatches is set to 1, that means that Casper will throw out any sequences with more than one mismatch. However, generally speaking, 4 is a good number because beyond 4 mismatches, it's unlikely you're going to see appreciable off-target activity, but 3 and 2 and 4 mismatch locations could potentially have high off-target scores. Next, you can check whether or not you want an average output or whether you want a detailed output. The average output will run a little bit faster for large data sets, but if you want to have a greater view of where the off-target hits are occurring, you can leave this unchecked. Lastly, you supply an output file name. We'll call it output1.txt, and then we can run the off-target. So we click the run, and the off-target will start, and it will show that it has been completed. Now we can click submit. And for these sequences, we got scores of 0. So we don't have any appreciable off-targets for these 5 sequences. Now, if we wanted to, let's say, order these guide RNA sequences from an oligo manufacturer, we can actually export these to a comma-separated file to make their manipulation and upload to those manufacturers' websites really easy. So all we have to do is export selected guide RNAs. This tells us where the file will be located. By default, it's in the database folder, and then you select the file name, exported guide RNAs 1, and we can export. And if we go and look in this folder, we can see exported guide RNAs 1, as well as our off-target output here. Off-target output shows that we didn't have any hits, and the exported guide RNAs can be opened in, whoops, sorry about that. The guide RNAs can be viewed in Excel and filtered or trimmed or manipulated in any way you would like. So that is a brief overview of single gene or locus guide RNA generation and export, and we hope this will be useful for all of your CRISPR applications.